Hello everyone, welcome back to our lectures. Today we'll be talking about the physical and chemical properties of alkenes. Just to remind you that in the last lecture we started talking about the unsaturated hydrocarbons, but today we'll be focusing on the physical and chemical properties of alkane. Let us take it off from there immediately. I have a beautiful quote for you from one of the greatest scientists that ever lived. He was a theoretical physicist. Was German-born, Swiss, American scientist, Albert Einstein. What did he say? Let's see. He says, life is like riding a bicycle. To keep your balance, you must keep moving. Albert Einstein of the blessed memory. Remember, he won the Nobel Prize in Science for his work in photoelectric effect in 1921. He was a great scientist indeed. All right, let's take it off immediately from there. Now, at the end of this lecture, we will achieve the following objectives. Number one, we'll understand the physical and chemical properties of alkenes. And two, we'll now write the equation for the additional reactions of alkenes. And then we also use a rule, what we call the Mcconnell Rule, to predict the major reaction product and draw the structural formulas as well. So those are the main two objectives we're going to be achieving in this lecture. Let's take it off from there. Now, physical properties of alkenes. Remember, again, the physical properties of alkenes are just like the physical properties of alkenes. Alkenes, of course, they're the second class of hydrocarbons. Of course, all the hydrocarbons only contain carbon to hydrogen. So this is like the simplest, ethene gas. Now, they contain only carbon to hydrogen. Remember again that a carbon to hydrogen bond is highly nonpolar, and as a result will be what? Hydrophobic, very insoluble in water. So their physical property is similar to those of alkenes. They are nonpolar and insoluble in water. Now, at room temperature, their physical properties changes from gas to solid and to gas to liquid and to solid. Again, showing that the unbranched ones are homologous series. So those ones that contain from carbon 2, that's from 18 to butene to carbon 4, are gases at room temperature. The ones that contain about 5 carbon to 17 carbons are liquids at room temperature, and whereas those of them that contain more than 18 carbons and more are solids at room temperature. Again, like I said, their density is less than that of water. They are less dense than water. So what it means is that if they're going to float in water. Now, the low molecular weight alkenes produce a kind of gasoline-like odors. Very, very unpleasant odor. Not really pleasant if you see how the gasoline smells. And then again, the boiling and melting point increases as the number of carbon increases. And the reason for this is that as the number of carbon increases, their molecular weight increases. And remember again, since these molecules are highly nonpolar, the only intermolecular force, the only IMF, intermolecular force they have is what? Is London dispersion force. And again, London dispersion force increases as the molecular weight increases. So that's exactly what is happening. So as the number of carbon increases, their boiling and melting point increases. What it means is that you are increasing the molecular weight. The molecular weight is increasing. The molecular weight will lead to the increase in London dispersion force. And the increase in London dispersion force result to increase in boiling and melting point. Again. All right. So these are all about their physical properties because we're not going to spend a lot of time because they don't have many of them. They are highly nonpolar. Now, let us go straight to their reactions. Now, the alkene reactions or their chemical properties. Alkenes are very chemically reactive. Now, they undergo both combustion. Remember, when we talked about alkenes, when we talked about alkenes, the only reactions that alkenes undergo is combustion. Now, let me tell you this. Every hydrocarbon, a hydrocarbon is any compound that contains hydrogen and oxygen. Remember, every hydrocarbon, just like alkene, every hydrocarbon will undergo combustion, whether it is an alkane, whether it is an alkene, or whether it is an alkyne or an aromatic. Every hydrocarbon will react with oxygen to form what? Carbon dioxide plus water. Just remember that. So every hydrocarbon, this can be an exam question as well. However, in this particular reactions, we're not going to be focusing on this because we've covered this already in the reactions of alkane. Our major focus is going to be on the addition reactions. So the addition reactions, that's what we'll be talking about. What are addition reactions? Addition reactions are those type of reactions in which a compound or a reagent adds to a multiple bond. A multiple bond can be a double or triple bond to saturate it. So a compound adds to the multiple bond to saturate it so that it's going to become single bond. And so remember again, this reaction takes place at that carbon to carbon double bond, just to make it saturated. Now, a good example is what I have here. Look at what I have here. Now, this is a prototype of alkene that has a double bond reacting with a diatomic molecule. This diatomic molecule has X and Y. So what's going to happen? They're going to share it. Now, look at the bond. The bond is going to be this way. Now, X will now go and add to this, whereas Y will go and add to this. At the end of the day, what happens here? Now, if you put X here and put Y here, this will become single bond. This bond goes from, okay, let me try to show you this, goes from double bond to single bond and becomes completely saturated with those atoms attached. So that's what we call addition reaction, as the name implies. When you add, you're not getting anything out. All of them adds to form one single molecule, just like you're adding 1 + 1 to give you 2. Now, there are 4 types of addition reaction we're going to be talking about. The first one is halogenation. Halogenation simply means addition of halogens. What are the halogens? The halogens, of course, are the group 7 element. You can add chlorine, iodine, bromine, and fluorine can all be added. Of course, you're adding them as what? As their molecule. So, okay, let me be writing them as Cl2. Let me give some space to do that. I should have written them as. Now, remember, most of halogens exist naturally as the atomic molecule. So, you're going to be adding them this way. You're going to be adding them this way. So, addition of these guys is what we call halogenation. Now, hydrogenation or reduction means addition of hydrogen. Here, you're adding hydrogen. Here, you're adding just a molecule of hydrogen to saturate this carbon to become single bond. Now, hydration means addition of water molecule. Hydrate, just water. So here you are adding H2O. Remember, H2O exists, is broken apart into hydrogen ion and hydroxy ion. So you can also write this way. So we are adding this as a single entity, OH, and H as a single entity in hydration to form, of course, alcohol. I'm going to show you this in the next slide. Then hydrohalogenation means addition of what? Hydrogen halide. A hydrogen halide is a just simple acid, whereby hydrogen, it could be HCl. Remember, this is a halogen, this is a hydrogen. That's what we call them, hydrogen halide. So HCl, it could be HI, it could be HF, it could be HBr. If you add them, they're going to saturate this. So these are the 4 classes of addition reactions we're going to see. Now, I have a beautiful reaction map for you here that explains these reactions of the reactions of alkenes. Now let's start. Okay, if you call this one number 1, here this is hydrogenation. If you have an alkane and you add hydrogen to it, you are saturating the bonds to form an alkane. That's exactly what happens here. In the second one, now alkene will react to any of this. Remember, I told you if you add any of the group 7, it is called halogenation. And when you add them, you form haloalkane. Haloalkane simply means an alkane that has some of the hydrogen that have been replaced with some atoms of the halogens. That's what we call them, the haloalkanes. Now, in this one, this is number 3. Hydration means addition of water. Here, remember again, you are adding water as H and OH. So one of the H adds to one of the double bonds. OH again, this OH adds to that double bond to form an alcohol. And we're going to come back to this by the time we get to the next module where we'll start talking about alcohol. And the last but not the least is hydrohalogenation. Again, addition of hydrogen halide. If you add a hydrogen halide could be HCl, it could be HBr, it could be HF, it could be, okay, I didn't write this, it could be HI, hydroiodic acid. Addition of this will also form haloalkane as well. Let's begin to take this one after the other. Let's look at hydrogenation. Addition of hydrogen, of course, it occurs in the presence of catalyst. Usually occurs in the presence of metallic catalyst, usually either palladium, platinum, palladium, or nickel. That's where it occurs. And then, now, this is actually the very application of making margarine or butter. Now, hydrogenation of vegetable oil. Vegetable oils are polyunsaturated. Vegetable oil are polyunsaturated for as you remember. We're going to talk about this by the time we get to fatty acid, but it's important to say. So they are the polyunsaturated fatty acid. So that means they have a lot of unsaturated carbons in them. So what happens? If you now put hydrogens to them and saturate them, they will go from liquid, which they wear as oils, to solid, which is what? Which is the butter or margarine. So hydrogenation of polyunsaturated molecules, oils, make them saturated and reduce their temperature. And this process is employed in the process of what? Margarine making or butter making. This is a very wonderful industrial application. Now look at what happens here. In this reaction, this is an easy reaction. Remember, H2 means there are two hydrogen atoms. One of them is going to add to this place, and the other one here is going to add to, okay, let me bring it down. So this is H and H. Remember, one of them will come here, and the other one will come here, making this completely saturated. Remember, a catalyst is involved. Now let's write the product. What will the product give us? We're going to have this. Nothing is happening here. Now look at where the reaction is taking place. There's a hydrogen here. Remember, we have another two hydrogen here before. Now what happens? Let's see what happens. I'm going to use a different color. Now there was addition of these two hydrogens. So one of them will go to this place and the other one will go to this carbon to saturate it. So basically this is an alkene at this point. When you saturate it, you form an alkane. That's exactly what we call addition of hydrogen or hydrogenation. Remember again, addition of hydrogen is also called reduction. It's also called reduction. So addition of hydrogen is also called reduction because remember when we talked about our review topic, we said addition of hydrogen is called reduction. Let's go to the second one, halogenation. Halogenation simply means addition of what? The group 7 element in their pure form. The fluorine, the chlorine, the bromine, and iodine. So the reaction between a halogen and a double bond resulting to carbon single bond. Of course, the product are what we call the haloalkanes. You call them either the haloalkanes or the alkyl halide. Let's see what happens again. This will break down into, okay, let me use my usual red. This will break down. This is usually Br, 2 BRs. What again happens? This one will add to this point. Not scrappy drawing. And this one will add to this point. Again, if I draw what I have left, what is formed, remember I have H here, and here I already have two hydrogens already. So what's going to happen? I'm going to use my green. I'm going to add one of the bromine is going to add here, and the other one is going to add here. So this is what we call this. Of course, this is an alkene. This is what we call a haloalkane. Or haloalkane means it has a halogen and it's an alkane because it's carbon to carbon single bonds everywhere. If you want to name this now, this is 1, 2, 3. You call this 1, 2 dibromo. This will be 1, 2 dibromo. I don't expect you to name it, particularly when I'm testing you on reactions. I don't usually want to mix it up with nomenclature, but at times I can do that. So this 1, 2 dibromo propane, 1, 2, 3. 3 is prop, and there are two bromine attached, like carbon 1 and carbon 2. All right, let's go to the next one. Now, before we go to the other last two reactions, there's an important concept we need to bring it now, because the type of addition reaction we're going to be talking about now does not involve what we call a homoatomic dimolecule. Here we're talking of we're talking of addition of something that is different. Now, so we call this Macrophage rule. Macrophage actually was a rule that was elucidated by Vladimir Vasilevich Mcconnell. He was a Russian chemist and a professor. So what he says that the rule says in addition of reaction that involves H and X. Now look at, there's hydrogen and another element. That another element can be a halogen, which is group 7 element. In the case of becoming an acid, it can be HCl, Hi, HBr, and HF, or OH. When you add H plus OH, it becomes water. So if you're going to add this molecule to an alkene, what happens? Hydrogen will be added to the double bonded carbon that already has more hydrogen. So hydrogen goes to the one that has more hydrogen, while the X here, which is another element apart from hydrogen, will now go to what? To the carbon that has less hydrogen. This is what we call Mcconnell Rule. No, so I usually call this the capitalist rule. This is actually the capitalist. I call this chemical capitalism. That's exactly what this rule is talking about. So what is happening? Now, this is important because it helps us to predict the major reaction product. That is the essence. This rule helps us to predict the major reaction product. So it helps us to predict the major reaction product. That's the importance of this. We're going to see how that plays out. So what is happening? Let me demonstrate Mcconnell Rule. So assuming I'm adding, like I said, I'm adding HX now, hydrogen, and connected to another element or group of, and another atom or group of atoms. In the case of water, because it's OH, that's why I say atom or group of atoms. Now look at what is happening. If you look at these two hydrogen, let's count. There are two. Remember, for a double bond to exist, there must be two carbons making it up. So there's a double bond there that is double. Let's count. Now, if you look at this one now, this carbon is connected to only one hydrogen. One hydrogen. Now, if you look at this one now, this carbon here is connected to how many hydrogen? It's connected to two hydrogens. Now, what is the rule saying? The rule is saying that hydrogen will be connected to the one that has more hydrogen already, whereas X will go to the one with less hydrogen. So what is going to happen? Hydrogen here will be connected to this carbon that already has more hydrogen, whereas X here will now go to this carbon. So if that happens, look at what you have. You now have, this is constant. Now, X now goes to this, then this becomes saturated, whereas hydrogen now goes to this. So what you basically have coming here now is this one is coming in at this point, and then another hydrogen, this one is coming in at this point. This is what we call the Mcconnell Rule. Now, why we are using the Mcconnell Rule is that this reaction can form another product. Now remember, this is the major product. This reaction can form a minor product, which usually in exam, when I ask you to do this reaction, don't give yourself a lot of work trying to first of all form. If you form the minor, you form the major, unless you have the time. Just go straight to give me the major reaction product. The minor reaction product here is going to be, okay, let me write it. It's going to be carbon. Let's see. It's going to be carbon to carbon to carbon. The minor reaction product will be doing it at random. You are not thinking of the rule. You can just take X and add here. So if you add X here, what is going to be? X is going to be here. And then you add what again? You now add your hydrogen at this point. Then hydrogen is going to be here. Then the rest, you saturate it yourself as it were earlier. So look at what you've done. In the minor reaction product, you added X at this point. You know, here we had hydrogen. And here you added hydrogen at this point. So this is actually the minor product. And in fact, this minor product is not quantitative, not enough of it usually forms. So in any time I ask you about the reaction that involves Mcconnell Rule, just give me the major reaction product. Let us take it off from there. Now, what is happening here? Now, addition of hydrogen halide obeys this. Addition of hydrogen halide or simple acid, or you can say they are binary acid, because most of them are simple. You can say they are binary acid as well. You can call them simple acid or even binary, because it's hydrogen and another element. Now, of course, obeys this rule. Let's see what happens here. Again, if you look at this, this has only one hydrogen. This has what? Two hydrogen. What is going to happen? What is going to happen here is that hydrogen, of course, will go here, and then chlorine will go this place to form this. So chlorine goes at this point, hydrogen comes at this point. This is the major reaction product. If you do the opposite, whereby you now take chlorine to add at this point and hydrogen to add, you form this, but this is what? The minor reaction product. Not enough of it is formed. And of course, if you want to name this, this is one. If you come from here, 1, 2, 3, 4. So this is, in carbon number 2, it's going to be 2-chlorobutane. And now this is going to be, of course, 1, 2, 3, 4. This is going to be 1-chlorobutane. So here, 1-chlorobutane is the minor product. This is the minor. Okay, I wrote it there. It's the minor product, and it's not going to form quantitatively enough to be made for you to isolate, whereas this will be the major product. That is what we call hydrohalogenation. Now, in hydration, the same thing occurs. Remember, water molecule is broken down into H. Remember, usually, water molecule, when you break it down, usually forms hydrogen ion plus OH minus. So you are adding two things. You're adding hydrogen ion and hydroxyl ion. So water molecule can be H2O or H and OH. It's split in such a manner that this one adds to one of the carbon, whereas OH also adds to that carbon. So we are treating this one as a single entity, which I called X earlier. So here, this is our X. Now, what happens? This reaction results to the formation of what? Alcohol. That is what actually. So what actually happens here is that the hydration of alkene results to the formation of alcohol, like I showed you in the reaction map. Again, this happens in the presence of an acid catalyst, and then it obeys the Macrophage rule. Again, let's see. Here again, remember, there's one hydrogen here. Here, there is two hydrogens. Now, remember, here we have H and OH to be added. I'm going to use a different color. So what it means is that here has less hydrogen. Hydrogen is going to add here because there's more hydrogen to this carbon, and whereas OH will now come and add at this point. And when you do that, what do you have? Now, let me draw the reaction product. The product is going to give us, I'm going to try to draw it here. We're going to have this, and then we are now saturating this bond. Remember earlier we had two hydrogens already connected to this. Now I'm going to use a different color. Now the hydrogen will be added to this point. Remember that. Whereas, okay, I also have one other hydrogen at this point, which I didn't write, so I'm going to write it. And then, yeah, okay, so I added my hydrogen at this point. So I'm going to use my green again to add my what? OH to this point. So the OH is going to be at this point. So you see, like I said, okay, this, yeah, the hydrogen goes to add here, whereas the what? The OH goes to add here. So this becomes the what? This molecule is alcohol. I'm not going to say the name because we've not done the nomenclature. So this is an alcohol. That is what this is. So hydration of alkenes will form alcohol, and it obeys what? The Mcconnell Rule. I'm not going to try to spend time drawing the minor reaction product. Like I told you, always give me the major reaction product. That is exactly what I need. Now let's begin to solve some problems immediately without much ado. It says use the Macrophage rule to predict the major reaction product of this reaction. In this case, I stated it the major reaction product. Again, in exam, I may not state it. Give me the major reaction product because they are what is quantitatively available at the end of the reaction. Okay, let's now look at the first thing you need to do is to make sure that you know that, look at the two carbon. Remember, there's carbon here and there's another carbon here. Now, this carbon now has 4 bonds, 1, 2, 3, 4. There's no hydrogen, but this one is 1, 2, 3. So it has to be saturated by hydrogen. So now look here, look at this one. If you look at this carbon now, it doesn't have hydrogen. Here has one hydrogen. What it means is that this is a hydrogen halide. Hydrogen, we want to go, this one, we want to go and add to this. Whereas the I itself, we want to go and add to this. Then we now draw the product. What would the product be? The product is going to be, I'm going to try to draw it the way it is. So remember, that's this one here. And then, again, remember, I'm not going to add. Now the I is going to go here. The iodide will go here. So I'm going to add my iodide at this point. This is the iodide. And then remember, there was H here already. Another H will be added. You can leave it like this, but if you want to show it, that's fine. You can just show that there is what? H added to this point. Remember again, before this time, there was H there originally, and another H was added. So if you count this now, 1, 2, 3, 4, the bond is 4, which is all saturated. So this is what we're going to form. Again, remember, this is what? A haloalkane. And you can name this as well, but I'm not going to be talking about the nomenclature. Remember, this will form haloalkane. So this is what? The first reaction here is hydrohalogenation, or addition of hydrogen halide. The second one is hydration. Addition of what? Is the addition of water. Remember, water will be broken down into this. So what's going to happen? Now, this is the same reaction. Here has no hydrogen. So what it means is that OH is going to go to add at this point, whereas hydrogen will come and add at this point, because here, like I showed you here, there's one hydrogen here. Now, what are we going to have? We're going to have this. Again, there is this methyl group attached here. And then now you're going to have an OH group at this point. and then of course you're going to have hydrogen attached at this point. Normally, we are not supposed to show this hydrogen in a shortcut, but I'm just showing it to make it clear. You are not supposed to, in a shortcut or in a skeletal structure, you're not supposed to show hydrogen. So if you drew this without showing me the hydrogen, so if you drew this, for me, that is okay. That's actually what it's supposed to be. But I'm just showing you this so that you understand the actual reaction and the way it is taking place. That is reflection 1. Let's take more reflection questions, because like I said, practice makes perfect. The more we practice and the more we try to draw these structures, the better we get at it. What is happening here? Let's see what's going on. Now, this is a summarized reaction of the 4 reactions. Remember, look at all of them. Hydration, addition of hydrogen. Bromination, which is halogenation, which is addition of halogen. Addition of water, hydration, addition of hydrogen halide. So this will be hydrohalogenation. So those are the things. So I'm going to start with the simple ones. Remember, the double bond is between here. Let's see. Remember here now, there's 1, 2, 3, 4 bond. There's no hydrogen here. But here, there should be hydrogen to saturate this. Let me use my usual red. So here, there will be 1 hydrogen. That's what it means. There's 1 hydrogen here. This 1, 2, 3. 1, 2, 3. Hydrogen makes it 4. So what are we going to have? If you add hydrogen, hydrogen will be added to this side. So what is going to form here will be look at what we're going to have. Already we have this methyl group here. Now remember, hydrogen can be added anywhere. It's some molecule. So I'm going to add 1 hydrogen at this point, and then add another hydrogen at this point. Remember, this hydrogen is implicit. You don't need to show it, but I'm just showing this one here to let you know. So there's already 1 hydrogen here. So you're going to have 1 of them here and 1 of them here. Remember, there's another one here too, but I'm not showing it because this is the skeletal structure. Let's go to the next one. In the next one, let me do bromination again, because bromination again does not require what? The first 2 I'm doing, they don't require the Macrophage rule. So that's why I'm doing them first. Now, again, there's a methyl group here. Now, bromine will add any of the 2 sides. So I'm going to add 1 of them. Oh, no, I'm going to change it. I want to use my green. So one of the, what is going on? Thought I got the green. Yeah, I got it now. So it's going to be BR, and then there's another BR here. This is what is going to form in this one. Now, this 2 is where we have to do the thinking. Remember, in these 2, the Macrophage rule is followed. Let's start with this one. I won't have enough space here, but I'm going to move it a little bit to the right. Now, in this one here, okay, I may have space. Okay. I'm going to try to redraw the molecule again. Remember, there's more in here now. Hydrogen will be added. Remember the rule? Hydrogen, we want to go to a place that has more hydrogen. So there's hydrogen here. Whereas iodine, we want to go to this side. So that's exactly what will happen. So what are we going to have? Put this methyl group. Iodine, we want to go to this place that doesn't have hydrogen at all. So what am I going to have? I'm going to use my green. I'm going to have iodine will be here, and then hydrogen is going to be here. So this is exactly what we're going to form. The same thing we go for hydration here. Water molecule. Remember, in hydration, you're having H and OH. No, I'm going to remove that because I don't even have enough space there. So remember, you're having H and OH. Yeah, that's what we have. So what are we going to have? Now look at what is going on. In this reaction now, OH we want to add here because there's no hydrogen there. So OH we want to add here. Whereas hydrogen itself, we want to add to this one. I'm not going to show you, but hydrogen is going to want to add to this side. So if you now draw the product, I'm going to draw it. So it's going to be, I'm going to have this again. Now I'm going to have this. Now remember, OH will be added to this point. So you're going to have your OH. No, I'm going to use my green. I'm going to use the green button. So it's going to have OH here. And then, of course, the hydrogen will be added at this point. So these are the major reaction product of this. So this, I usually give my students this even in the worksheet and sometimes in exam. This summarizes all the reactions, all the additional reactions of alkene. And like I said, it is only the hydration and hydrohalogenation that requires Macrophage rule. The ones that I have to do with diatomic, homatomic molecules like hydrogen and bromine does not have to use the Macrophage rule. Let us now go to the next problem. In the next problem, it says, complete the following reaction. Again, look at what is happening here. Remember, the ones we've been doing, we've been using 1 mole of the reagent, 1 mole of the reagent. Now here, there are 2 double bonds. What does that tell you? It's going to need 2 moles. So here there are 2 double bonds. So you need 2 moles of each of the reagents for the product to form. Let us finish. So we're going to try to saturate it to the end. So now let's see. Let's count. How do we count first? Here, 1, 2, 3, 4. There's no hydrogen here. This one, there is 1 hydrogen. Okay, let me use red. There's 1 hydrogen here. Again, let's look at these 2. Here again, 1, 2, 3. That means there's 1 hydrogen here. Here, 1, 2. There is 2 hydrogen here. Here now, there's carbon here. There will be 2 hydrogens here. So this is the first thing you need to do. Know the number of hydrogens that you have there. Having done that, the next thing we do is start drawing the product. Remember, in any of them, hydrogen, bromine, you want to go to this place that has less hydrogen and this place. So if I draw it, it's going to be, if I put this one there, and then I put this down. Remember, bromine, we want to add to this point. So, okay, I can put my bromine. Okay, I have an idea to save my space. I'm going to do this. So I'm going to make this one a little bit like this. And then I'm going to add my bromine immediately at this point. My bromine goes here. And where my hydrogen goes here. So remember, again, so this is going to be this. So remember, the hydrogen, the first hydrogen, there's a hydrogen here already implicit. But the other hydrogen coming from here is going to go here. You know, I'm going to use this. It's going to go here. What is going on? It's going to go here. Wait. Okay. Good. I've done the first one, saturated. I'm going to first the second one. In the second one, what's going to happen? So remember, there's a methyl group here. I'm going to add this one again. Now, this is another one we're going to be dealing with. There's 1 hydrogen at this point. There are 2 hydrogen at this point. What it means is another bromine molecule will be added at this point, and hydrogen will be added at this point. So what's going to happen? I'm not going to show the hydrogen is implicit here. It's already added, but I'm just going to show the bromine where it is added at this point. So the bromine, again, will be added at this point. Remember, there's already 2 hydrogen here plus another one added. Okay, let me just add that one. There will be 1 hydrogen that's added. But remember, ab initio, there were other 2 hydrogens already there, just to saturate it. Just to remember that. All right? Like here again, there's hydrogen already, remember? So, but you don't need to show that. This is this is the skeletal structure. You don't need to show those hydrogens for me. So now let's do something here. Here again, there will be 2 moles of water molecule that will be used to reduce this to form alcohol. Remember again, this is a haloalkane. This is a haloalkane. Haloalkane. Now, so this is going to be an ethanol. All right, let's see what's going to happen here. Again, we've already done our homework here. There's no hydrogen. So OH is going to want to add at this point. So I'm going to start drawing that. It's going to be this. OH, we want to add at this point because there's no hydrogen there. Okay, I think I'm trying to undo, then get my green. Therefore, so I'm going to get my OH at this point. So my OH will be here, and then I get my red again. I keep drawing the molecule. So if I put this one down, remember the hydrogen is going to be here. I'm going to add 1. The hydrogen that comes will go in here. There's an old one there before, which is implicit when I did the counting, but one of them will be added here. Then I go to the next bond. In the next bond, I'm going to use my red again. In the next bond, so there is this thing here, and I have this here. Now, again, the other one is between these 2. Again, I'm not going to put the hydrogens again. Like I said, it's implicit in a skeletal structure. I'm just going to go straight to tell you where the OH group is located. So the OH group is going to be this again. So here, there are 2 molecules of water that was added to saturate this because there are 2 of the double bond. Here, there is 2 molecules of hydrogen bromide or hydrobromic acid to saturate this as well. Again, this is an alcohol that is formed, an alcohol, and this is haloalkane. No need to name it because I didn't ask you to name it in this problem. That is not our focus. We'll now go to the next problem. Now, I have a lot of problems here because students usually struggle with this. That's why I put more emphasis in. Now, this one is a little bit different. It says, identify and draw the missing reactant. Now, we're going to work it from behind. What is the missing reactant? Of course, we're talking about alkenes. They're all going to be alkenes. But what are you going to do? Now, if you want to draw it behind, let me give you a secret. Drawing the reactions behind, you're going to be using these 2 reactions. This is a hydrohalogen. a hydrohalogen HCl, this is water. Both of them requires the Markov. In the Rey reaction, both of them requires Markovnikov's rule. Now, look at what's happening. We're going to apply the reverse. To solve it behind, you're going to do what we call the reverse of the Markovnikov's rule. The reverse of the rule. So we're going to use the reverse of the Markovnikov's rule. What are we going to do? Look at how that works. Now, double bond is between two carbons. So this can add to this, it can add to this. So what it means is that we are removing a double bond. You're actually eliminating this and one hydrogen. We don't know where. How do we know where? Now, this can add between this and this. But what determines where you add it is the reverse rule is you now count the number of hydrogen between the two carbons now. Remember before we counted with Markovnikov's rule, we counted the number of hydrogens in each of the carbon. No, we're not doing it in the reverse. In the reverse, you are counting the number of hydrogen between the two carbons. So let's look at this carbon now and this carbon. How many hydrogen does it have? It has 1 hydrogen plus 3, which is 4. This one has between this and this 1 plus 3, which is 4. What does this tell you? It doesn't matter anywhere you add it, because the number of hydrogen between these two, this carbon and this and this and this are equal. So if that means I'm going to take this one off and take the one off and add it to any of them, either this way or that way. So whichever one you do it, it doesn't matter. So I'm going to write it here. I'm going to have H here. This is the first one here. It doesn't concern. Now I say you can add it anywhere. So I'm going to add it between the first two. So if I add the double bond between these two, and then to saturate this, remember there's one hydrogen. You are removing just this and this. So there'll be one hydrogen left here, and then there's that hydrogen left here. That's exactly what you are doing. So you are removing, what we're basically doing is that you are removing that thing you added. So I removed this and this. That's exactly what happened. So in this case, okay, no, not this and this, because here we also, so what I basically removed is I removed this and this. That's exactly what I removed. So let me tell you the ones that were removed there. Removed this one and this one to form that. That's exactly what happened there. So exactly something is what we're going to consider. But this one, remember this one, when we counted, we have between this one 4, between these two, there were 4 hydrogens. And between this and this, there were also 4 hydrogens. So it doesn't matter what added. In this case, this one is different. Let's count again. If you look at this one, let's see what's going on. Between this and this is addition of water molecule. So that means we're going to have an alkene to form water. Let's look at what is happening. Now, between this one and this one, how many hydrogens do we have here? We have 3 plus 1 is 4 hydrogens. Okay, let's count. Again, between, we counted this carbon. What about between this carbon and this carbon? Oh, we have 2 hydrogens. 1 and 1 is 2 hydrogens. What it's telling us is that the double bond, when you remove one molecule of water, the double bond is going to be added in between this and this carbon, not this one that has too many hydrogens. So it's going to be added between this carbon and this carbon. So we're going to be removing this one and, okay, let me use a different color. I'm going to be removing this and this as to water molecule, which is the reverse of the rule. So let's go back and finish it. So I'm going to have H3C, nothing concerns this one. Then here, remember I told you the double bond is going to be added at this point. So I'm going to add the double bond here. If you add the double bond here, this hydrogen has been gone. So you have CH3 here. 1, 2, 3, 4, carbon is satisfied. You now put this. Remember, this OH group is gone. So what it means is that you now have this. It's gone, but you still have one hydrogen attached to it. So you still have one hydrogen down here. You can put it this way, or you can use a bond and put it, doesn't matter. So this is exactly what it means is that you're going to start with this, react with this to form this product, which is remember again, this is an alcohol, because addition of water to an alkene forms an alcohol. Here, this is again a haloalkane. Haloalkane. Because addition of hydrochloric acid to an alkane will form a haloalkane. This is exactly what they are. Now we're going to be going to the last but not the least of the problems we're going to be doing. It says, what are the reagents used to make the following product? These are the following. Used to make them. So they are the product from the reactions of 2-pentane. Now, so I made it in such a way that it will be a particular alkene that we start from. So we're starting with alkene. So let's draw it. So what it means is that we're going to be working this behind. So we're going to be doing working everything behind. That's exactly what we're doing here now. Like we did before. So we're going to be working, this is the product. So what are we going to add? That's exactly what, so what are we going to be adding to the reagent? So the reagent I have here is 2-pentene. Let me draw it. 2-pentene is C, 1, 2, 3, 4, 5. 2-pentene means is in carbon, is in between 2 and 3. So this is going to be, here is going to be one hydrogen here. Then this is going to be satisfied. And then this. So this is 2-pentene, because here the carbon is in between 2 and it doesn't have any attachment. So it's an unbranched alkene. Now, it says, okay, what are you going to add to this? So we're going to say plus, we're going to be adding, what are you going to add this to form this? It's easy. You have 2 molecules of bromine. So that's tell you easy. You're going to be adding what? Bromine. Here, remember, you're going to be having 2-pentene plus bromine to form this. So what we're adding here, the reagent here is bromine. So what are the reagents? So the reagent here is bromine gas. That's what you're going to be adding in this one. Okay. Let me not take too many space with that block. Okay. So the first one is bromine for this one. So A here is bromine. B, what are we going to add to have this? Look at this. What did we add to have this? This was completely saturated. What it means is that you only added hydrogen. So here we're going to be adding hydrogen gas, H2. That's what we're going to be adding at this point, hydrogen gas. Because you saturate this completely to form this. Now, what about this? Look at this now. What did you add to this? Here, you now added something here to become chlorine. What it means, here has one hydrogen plus another one. So that means there's another hydrogen here added. So you added H and Cl. So what did you add here? We're going to be adding HCl. If you add HCl, remember again, the reaction will be the Cl here is going to go to this one. Whereas here, okay, the Cartan number, here, remember this reaction now will not, this one will not involve Macrophage rule, because the number of carbon in both of them is equal. So it doesn't matter where you add it. From what I have here, this Cl will be added here, and this hydrogen was added here to form this. And the last, but not the least, before we end this lecture, is this one. So here, what are we doing? Now, there's OH group that was added here. That's what it shows. We have one hydrogen, one OH group added here. And then here was hydrogen. Remember, here's one hydrogen, another one was added there too. So what that simply tells us is what? What it tells us is that it was a hydrogen too added. So it added hydrogen here and OH here. So if you add OH and hydrogen, that's water molecule. So this is just water. You can write it this way. You can write it as HOH. So what are the reagents? In the first one, to form this product, bromine was added in A. In B, hydrogen was added to completely saturate it. Then C, to form the haloalkane here, HCl was added. And then finally, to form alcohol, which is water molecule, was added in part D. And having said that, we've come to the end of this lecture. Thank you again for listening. Bye.